And the third signal assignment is a selected signal assignment. In this assignment, you say with some expression select. I have my signal name gets the value of some signal value when my expression equals condition 1. It gets the second signal value when the expression equals condition 2. However many conditions I have, and then the last one, I have a signal or value when others. Thus saying when my expression is not any one of the conditions I've listed, then the final signal value is assigned. So here's an example of that. With SEL, select. Q gets the value of A when LCL is equal to 0. Q gets the value of B when SEL is 0, 1. Q gets the value of C when SEL is 1, 0. And if SEL is not any of those three values, then Q gets the value of D. Now why could we not just say 1, 1 for D? Well, the reason we have to do that is because if select is a standard logic vector, or standard logic, that means there are 9 different values that select can be, 0 and 1 being only 2 of those. So VHDL has to consider those other values when it's executing this statement. So to cover all those possible values, you just use the when others as your default clause. The logic that gets generated in this case is a wide mux. Unlike the previous statement where I had a series of priority muxes, in this case all values have an equal chance of being true. It just depends on what select is. So there is no priority associated with the selected signal assignment. In VHDL, you can also specify delay when you make your signal assignments. There are two ways or two types of delay that you can specify, what's called the inertial delay and the transport delay. To specify an inertial delay, you can use the after clause. So for example, I can say A gets the value of B after 10 nanoseconds. So if B transitions, the statement must wait 10 nanoseconds before it can apply that signal to A. Now the inertial delay is the default, and what that means is that if B pulses, and that pulses in a short duration, then essentially the statement filters it out. That pulse is not propagated. The other type of delay is the transport delay. With the transport delay, you use the keyword transport before your expression. That tells the tool that regardless of how short the pulse is for B, that pulse is transmitted to A. Now the timing for what is considered a short pulse is usually handled by the simulation tool. So you should check your simulation tool to see exactly how to adjust this value if you want. As a note, the after clause, again as we said earlier, is a simulation construct. So the synthesis tools will not be able to synthesize a particular timing delay into your hardware. Now the simple signal assignment, the selected signal assignment, and the conditional signal assignment are all examples of implicit processes. The explicit process statement is when you use the keyword process to create a process. The process then executes infinitely unless you use a sensitivity list to break its execution or you have wait statements inside. Essentially, if you have a sensitivity list, that implies a wait statement at the end of the process. Inside of an explicit process, the statements are executed sequentially. So again, since the explicit process is a process, it's executing concurrently with other processes in the architecture, but the statements inside of the process are executing sequentially. Looking at the structure of the process, you can assign a label to the process, giving it a unique name. The process can have its own declarations, constants, types, or variable declarations, and we'll talk about variables in a little bit. Anything declared within the process declaration section would only be locally visible or visible just within the process. Then the process has a begin keyword followed by the sequential statements followed by the end process. If you use a label, then you can say end process and then the label name. Here are two examples of explicit processes. The first process is assigned the label process 1 and it is sensitive to A and B. Thus, if A or B changes, the process turns on and executes the sequential statements inside. Once it is done executing those statements, it will wait for another transition on A or B to execute the process again. In the second example, process 2, this example does not have a sensitivity list, so this process begins executing immediately at the start of simulation. Again, the statements inside are executed sequentially. This time, when the process reaches the end, a wait on statement is seen. This wait on statement forces the process to wait until A or B transitions before the process loops around and begins executing again. While the behavior of these two processes may seem different, they are actually identical. This is because all processes begin executing at the start of simulation in order to define the initial output values. Thus, it's during the second iteration of process 1 when the sensitivity list starts controlling its execution. Thus, as was seen in the previous slide, having a sensitivity list is said to imply having a wait on statement at the end of the process since their behavior is the same. Having a sensitivity list and wait statements inside the same process is not legal in VHDL. Sequential statements are statements that are used inside of explicit processes. Almost all of them, except for the simple signal assignment, can only be used inside of explicit processes. They're used to indicate the behavior of the logic inside as well as express an order to it. Examples of sequential statements are the simple signal assignment, the if-then statement, the case statement, looping statements, and wait statements. The simple signal assignment is the same as the simple signal assignment we discussed before, but it's also allowed to be used inside of an explicit process. The if-then statement allows us to do selection. The format is if some condition is true, then you have a sequence of statements that are evaluated. Else if condition 1 is not true, then condition 2 is true, then we execute another sequence of statements. If none of the conditions above are true, then I can have a final else which will default to a sequence of statements and execute those. So here's an example of that being used. We have a process that is sensitive to select A, select B, A, B, or C. If any one of those changes, the process turns on and tests to see if select A is 1. If it is 1, then Q is assigned the value of A. If select A is not 1, then it tests to see if select B is 1. If it is, then Q is equal to value of B. If that is not true, then Q is assigned a value of C. So again, notice that we have a series of priority muxes. Whereas before, with the conditional signal assignment, that was a implied process on its own. The if-then-else structure is a sequential statement, so it can only be used inside of a process. So again, to reiterate, the conditional signal assignment is a process on its own and cannot be used inside of an explicit process. The if-then-else statement is a sequential statement, so it must be used inside of a process and cannot be used on its own. The next statement, sequential statement, is the case statement. With the case statement, you type the keyword case followed by some expression is, and then a series of when conditions. When condition 1 is true, then a sequence of statements is executed. When condition of true is true, then a sequence of statement is executed. Have as many conditions as you need. The when others clause is at the end, is optional to indicate a default state, and of course those sequence of statements will be executed then. So here's an example. We have a process sensitive to select A, B, C, and D. The case statement is testing for select, and if select is zeros, Q is equal to the value of A. If it's 1, it's equal to the value of B. If it's 1, 0, it's the value of C. And if none of those are true, the when others clause indicates that Q gets the value of D. Again, select, if it's a standard logic, has 9 different values that each bit can be. So even though it seems like we've covered all the cases, we've actually only covered a fraction of the possible conditions for select. So the when others clause is used to cover all the others. The logic that is generated is the 4-input mux, similar to the logic that is generated for the selected signal assignment. Like the if statement in the conditional signal assignment, the case statement is a sequential statement that must go inside of an explicit process. The selected signal assignment is an implied process on its own and cannot go inside of an explicit process. VHDL has support for loops. So there's 3 different types of loops that are supported. First is the loop statement, which just indicates that the sequential statements that follow execute infinitely unless a nexus statement is reached, which you can indicate using some sort of condition to drop out of the loop, or a next clause, which indicates some condition for which the loop will stop executing the current execution and skip and proceed with the next execution of the loop. The while loop uses a condition to indicate how long the loop will continue to execute. So while the condition is true, the loop will continue to execute. When the condition is false, then the loop will end. The for loop allows you to indicate a certain number of iterations. So you can say for some identifier in some range and a sequence of statements. So for example, my range could be 0 to 5. And so my for loop then would make 6 iterations before the loop would exit. As a note, the next and the exit statements can be used in any of the loop types. And all loop types end with the keywords end loop.